There's a smell you know. You've felt it before. Standing near the ocean, that sharp, wet, alive scent that hits you when the wind comes off the water. Scientists have a name for the molecule responsible: dimethyl sulfide. It's produced by marine phytoplankton, by bacteria, by living organisms in the sea. On Earth, nothing else makes it at scale. Nothing geological, nothing volcanic, nothing chemical that doesn't involve life. And in April of 2025, James Webb Space Telescope detected it, or something that looks exactly like it, in the atmosphere of a planet 124 light-years from Earth. NASA did not hold a press conference. There was no announcement from the White House. No live broadcast. What the agency put out was a carefully worded statement that said, essentially, we would need multiple converging lines of evidence from multiple missions before making any claims. That's the official line. More evidence needed. More analysis required. More time. Meanwhile, the telescope that costs $10 billion, built by the most powerful space agency in history, had just delivered its data, and the people reading that data went very, very quiet. This is the story of K2-18b. And it's more complicated, more contested, and more genuinely unresolved than almost anything being reported about it right now. If you want to follow stories like this as they develop, real science, actual data, no manufactured hype, hit subscribe and turn on notifications. There's a lot more coming. K2-18b was found in 2015. Not by James Webb, not by some cutting-edge instrument designed for the job, by Kepler. Specifically by Kepler in the second phase of its mission, operating on only 2 of its original 4 gyroscopes after a mechanical failure nearly killed the spacecraft. A half-broken telescope, limping along on reduced capacity, found one of the most significant planets ever catalogued. That detail tends to get left out. The planet sits in the constellation Leo, orbiting a red dwarf star. Not a star like our Sun, smaller, cooler, burning a deep reddish-orange rather than yellow-white. K2-18b's year lasts just 32.9 days. It's 8.6 times the mass of Earth and 2.6 times the size. That combination puts it in a category that doesn't exist in our solar system. It's not rocky like Earth. It's not a gas giant like Jupiter. It's something in between. A sub-Neptune, a world with no local equivalent and therefore no easy analogy for what its surface, if it has one, might actually look like. But here's the thing that mattered from the start. It sits in the habitable zone of its star, the region where temperatures could allow liquid water to exist on or near a planet's surface. That's not a guarantee of anything. Plenty of planets sit in habitable zones and are uninhabitable for a dozen other reasons. But it kept K2-18b on the list of planets worth watching. In 2017, follow-up observations with NASA's Spitzer telescope refined the planet's mass and confirmed it as a genuine habitable zone world. Then, in 2019, the Hubble Space Telescope detected water vapor in its atmosphere. Water vapor on a planet in a habitable zone. That combination triggered global headlines, and K2-18b went from an interesting data point to a genuine target. Then James Webb launched on Christmas Day, 2021, and among its first priority observation targets, K2-18b. One James Webb Transit observation of this planet, it turned out, delivered the equivalent precision of 8 separate Hubble observations conducted over several years. That's not a metaphor for how powerful Webb is. That's the actual ratio Madhusudan's team calculated from the data. 8-to-1. So when Webb finally looked at K2-18b, what it saw was sharper, deeper, and more chemically detailed than anything Hubble could have produced in a decade of trying. September 2023, James Webb's first results from K2-18b are published. Methane confirmed. Carbon dioxide confirmed. Ammonia notably absent, which matters, because on a planet with a thick hydrogen atmosphere and no ocean, you'd expect ammonia to be present. Its absence is exactly what you'd predict if a water ocean were sitting beneath the atmosphere and absorbing it. The data fit what theorists had been calling a Hycean world, a portmanteau of hydrogen and ocean, a hypothetical class of planet with a dense hydrogen-rich atmosphere pressing down on a global liquid water sea. This finding was genuinely significant. And, honestly, it got less attention than it deserved at the time because of what appeared in the footnotes of the same paper. Almost as an afterthought, the team mentioned the faint signal. In the near-infrared data, there was a hint of something else, something at 1 sigma confidence, statistically too weak to announce, barely above noise level. They named it dimethyl sulfide, DMS, the molecule that makes the sea smell like the sea. 1 sigma means roughly a 30% chance the signal is a random fluke. You don't announce 1 sigma, the team didn't. They buried the mention in the fine print and noted it needed more investigation. Almost nobody picked up on it. But here's where it gets strange. The Cambridge team, led by Professor Niku Madhusudan, didn't drop it. They went back. This time they used a different instrument entirely, Webb's MIRI spectrograph, operating in the mid-infrared range, a completely separate detector covering completely different wavelengths than the first observation. 2 instruments. 2 independent wavelength ranges. The logic being, if the DMS signal is real, it should show up again, differently, with different hardware. If it's noise or an artifact of the first instrument, it won't. And in April of 2025, they published the result in the Astrophysical Journal Letters. The signal showed up again, DMS, and alongside it, DMDS, dimethyl disulfide, a related molecule produced on Earth by bacteria during decomposition. This time, the combined confidence reached 3 sigma. 3 sigma means a 3 in 1,000 chance the detection is a statistical fluke. In most fields, that's considered a meaningful result. In physics and astronomy, the gold standard is 5 sigma, a 1 in 3.5 million chance of a fluke, but 3 sigma is not nothing. 2 independent instruments, 2 separate wavelength ranges, the same life-associated molecules, detected back to back. Professor Madhusudan stood in front of a room of scientists at Cambridge and described presenting these findings as entering a lion's den. He knew the scrutiny was coming. At a press conference in March 2025, he said it plainly, "These are the first hints we are seeing of an alien world that is possibly inhabited." He told the BBC, "This is the strongest evidence yet. There is possibly life out there. I can realistically say that we can confirm this signal within 1 to 2 years. That's not a cautious scientist hedging his bets. That's a researcher who believes he found something. And now the second part of this story. Because this is where it gets more complicated, not less. Within weeks of the Cambridge paper publishing, the rebuttals started arriving. Not from fringe commentators, from other astronomers, from people with their own JWST data, their own statistical frameworks, their own interpretation of the same raw numbers. And 2 of the most prominent critics were, and this detail matters, former students of Madhusudan himself. Louise Wellbanks, now a postdoctoral researcher at Arizona State University, and Matthew Nixon at the University of Maryland. They had trained under the man whose conclusions they were now directly contradicting. Wellbanks and his team ran the K2-18b data through what they called an agnostic retrieval approach, a method that doesn't assume a particular set of molecules and instead tests every plausible atmospheric composition against the observations. Their conclusion, published as a preprint shortly after the Cambridge paper, under their statistical models, claims of a potential biosignature detection vanish. The DMS signal, they argued, disappeared entirely when you expanded the molecular library and didn't lock the analysis into a specific model. Other sulfur-containing molecules and hydrocarbons share overlapping spectral features at the exact wavelengths where DMS was supposedly detected. The data couldn't distinguish between them. Then came Kevin Stevenson's team at American University in Washington. Their paper, published in August 2025 in the Astronomical Journal, was titled, "Without Ambiguity, K2-18b does not meet the standards of evidence for life." They ran the MIRI data through multiple different reduction and binning schemes, different ways of processing the raw telescope output into usable spectral data, and they found that 87.5% of their retrievals showed no DMS signal at all. Not a weaker signal. 0 signal. The detection, they argued, only appeared under the specific data reduction choices made by the Cambridge team. Change the choices, the molecule disappears. Their conclusion, there is, as yet, no statistically significant evidence for biosignatures in the atmosphere of K2-18b. The mid-infrared data, they wrote, is plagued by red noise, random instrumental fluctuations that can look like real spectral features if you're not accounting for them correctly. And this wasn't just one team saying it. Rafael Luca, a postdoctoral researcher at the University of Chicago, published a separate analysis alongside colleagues that jointly examined the full panchromatic spectrum, the near-infrared data and the mid-infrared data together, and found that various molecules with methyl functional groups provide an equally good fit to the observations, meaning the data is not uniquely explained by DMS. Other carbon and sulfur molecules, none of them produced exclusively by life, can explain what James Webb detected just as well. The identification of the specific molecule, they argued, is what's failing, not the detection of an absorption feature, but the interpretation of which molecule caused it. Madhusudan's counter-argument is not that the skeptics are wrong to be skeptical, it's that the detection methodology matters. His team used 3 separate James Webb instruments, NIRISIS, NIRISPEC, and MIRI, and found consistent evidence across all 3 at different wavelengths. The argument that a false signal would appear independently across 3 detectors covering different parts of the infrared spectrum is harder to dismiss than a single instrument detection. And he's pointed out that DMS, specifically, requires a minimum concentration in a planet's atmosphere to be detectable, concentrations significantly higher than what other hydrocarbon contaminants would produce at these temperatures. If it's a fake signal caused by other molecules, the data should show those other molecules at levels that don't match K2-18b's known atmospheric chemistry. He says it doesn't. That argument hasn't been settled. It's actively ongoing in the peer-reviewed literature as of this year. And then, this is the part that slipped past almost everyone. NASA itself weighed in. Dr. Renyu Hu at NASA's Jet Propulsion Laboratory led an independent reanalysis, published July 2025, that combined 4 new James Webb observations of K2-18b transiting its star with the original Cambridge data. 3 separate teams applied 3 separate Bayesian statistical frameworks, each developing their own interpretation without coordinating conclusions. The result, the DMS signal dropped from 3 sigma to 2.7 sigma, below the original claim, still above what you'd call nothing, but weakened. And the official NASA statement that accompanied the study said, "We would need follow-up studies and multiple converging lines of evidence to confirm true biosignatures and rule out false positives, possibly including independent data from multiple missions and extensive atmospheric modeling." That's a very specific sentence. It doesn't say they found nothing. It says the bar is higher than what's currently on the table, which is a different statement. Now stop and sit with something for a moment. The ocean on K2-18b, that part got confirmed. Not the life signal, the ocean. In July 2025, the same period when the DMS debate was raging, a separate study confirmed that K2-18b's atmosphere is so rich in water that it may comprise as much as half the planet's entire mass. Half. Not a trace of water vapor in a thin atmosphere like Hubble first found in 2019. An ocean world. A planet where water may not be a feature of the landscape. It may be the landscape. No continents, no land, just a global sea of unknown depth under a sky dense with hydrogen gas. That confirmation didn't make the debate smaller. It made it harder to walk away from. Because if K2-18b has a hydrogen-rich atmosphere over a global liquid water ocean, at temperatures and pressures comparable to Earth's oceans, that's the exact environment where marine phytoplankton thrive on this planet. That's the exact environment where DMS gets produced on Earth. The Hycean world model, proposed by Madhusudan before any Webb data existed, fits the confirmed atmospheric chemistry almost perfectly, and that makes the disputed DMS signal simultaneously more plausible and more contested, depending on which part of the evidence you weight more heavily. Co-author Subhajit Sarkar of Cardiff University described it in the Cambridge press release this way. The inference of these biosignature molecules poses profound questions concerning the processes that might be producing them. That's a careful sentence. He's not saying it's life. He's saying if something is making this signal, we need to figure out what. Because here's the part that hasn't gotten resolved. The concentrations of DMS that James Webb detected on K2-18, if the signal is real, are orders of magnitude higher than on Earth. Modeling by the research team of Shengmin Tsai in 2024 calculated that maintaining detectable DMS at those concentrations would require biological activity approximately 20 times greater than all of Earth's marine life combined. 20 times. That's not a quiet ocean, that's an entire planet churning with life if the numbers hold. And if the signal is not real, then it's noise. And James Webb's mid-infrared instrument has a calibration sensitivity problem at certain wavelengths that nobody has fully characterized yet. Both of those things are currently true at the same time. There's a case from 1996 that scientists in this field bring up constantly, almost as a kind of warning: a Martian meteorite, catalog number ALH84P01, collected from Antarctica in 1984, analyzed for years. In August of that year, a NASA team published a paper claiming the rock contained possible evidence of ancient microbial fossils, tiny structures, chemical signatures, features that looked biological. President Clinton made a statement. NASA held a press conference. The world briefly believed Mars might once have had life. Over the following decade, each claimed biosignature in that rock was individually challenged and offered a non-biological explanation. The structures were too small to be cells. The chemistry had alternative sources. The temperature conditions when the features formed were inconsistent with life. The consensus shifted toward probably not biological. Probably abiotic chemistry that mimics biology closely enough to fool initial analysis. That case is still technically open. 28 years later, no consensus. Never confirmed, never fully dismissed. K2-18b is following the same pattern with uncanny precision, extraordinary initial claim, rapid institutional caution, immediate independent challenges, cascading reanalyses, no clean resolution. The difference is that K2-18b is still being actively observed. The meteorite is in a cabinet. The planet is up there, and the telescope is still running. In February of 2026, researchers made a decision that tells you everything about how seriously the scientific community is taking K2-18b, even amid the disputed DMS signal. They pointed radio telescopes at it, not just any radio telescopes. The Carl G. Jansky Very Large Array in New Mexico, one of the most sensitive radio observatories on Earth, and the Mir K2 telescope in South Africa. Both aimed at K2-18b's star system in a coordinated multi-epoch search, meaning multiple separate observation sessions over time, looking for narrowband radio signals. The kind of signals that, on Earth, would be produced by technology. Artificial transmissions. The kind of thing a civilization would emit. They found nothing. No narrowband techno-signatures at frequency levels equivalent to our own technology. But the decision to point SETI instruments at K2-18b at all, mid-debate, while the biosignature question is still unresolved, that's not a routine choice. You don't commit the VLA and Meerkat to a coordinated multi-epoch search of a specific planetary system because the data is inconclusive and you're filing it away. That's a decision that says this target is live enough to warrant the investment. Meanwhile, Madhusudan hasn't walked his findings back. As of 2025, he told the BBC directly, "I can realistically say that we can confirm this signal within 1 to 2 years." His team has stated that 16 to 24 additional hours of James Webb observation time could push the DMS signal to 5 sigma, the gold standard, the threshold where a detection in physics and astronomy is considered confirmed. That's not a lot of telescope time. For context, James Webb recently allocated observation campaigns lasting dozens of hours on individual targets. Whether K2-18b gets that time, and what it shows if it does, is, as of now, unknown. Here's the part that should stop being abstract, and isn't. The molecule at the center of this debate, dimethyl sulfide, you've already encountered it. If you've been near the ocean. If you've stood at a beach and noticed that salt and something alive smell that doesn't have a simple name. That's partly DMS. Marine phytoplankton in Earth's oceans produce it in enormous quantities, constantly, as a byproduct of their biology. They release it into the air. It rises into the atmosphere. It gets detected by instruments. It gives the sea its smell. James Webb, a telescope parked 1 million miles from Earth, looking across 124 light-years of space, detected absorption features at exactly the wavelengths where DMS leaves its fingerprint. In the atmosphere of a planet that may have a global ocean, at concentrations far higher than Earth's atmosphere contains. If you've ever stood near the sea and breathed in, you've already had a small, personal encounter with the molecule that's now at the center of the biggest unresolved question in modern astronomy. The molecule that only life makes. The molecule James Webb found 124 light-years away. Whether it's actually there or not is the question nobody can currently answer with certainty, and the fact that it can't be answered yet, with the most powerful space telescope ever built, after years of observation and dozens of independent analyses, should tell you something about how hard this problem actually is. Right now, in July of 2026, this is where things stand. K2-18b is the most studied habitable zone exoplanet in history. The methane is confirmed. The carbon dioxide is confirmed. The water-rich atmosphere confirmed at a level where water may account for as much as half the planet's total mass. The ocean world model is consistent with everything James Webb has returned across multiple independent analyses. None of that is disputed. The planet is, by every confirmed measurement, exactly the kind of world where life as we understand it could theoretically exist. The DMS signal is disputed, not resolved, not definitively confirmed, not definitively debunked. Stevenson's team says 87.5% of their data retrievals show nothing. Madhusudan's team says 2 independent instruments detected it across 2 separate wavelength ranges, and that's not a coincidence. NASA's Renyu Hu sits in the middle, saying the signal dropped to 2.7 sigma, and more data is needed before any claims. 3 positions. 3 interpretations of the same telescope output. All 3 positions currently exist simultaneously in the published scientific literature. The scientific community is also now debating something deeper than just K2-18b specifically, the question of whether humanity's current instruments are even capable of confirming a biosignature at 124 light-years distance. The 5 sigma threshold requires a signal-to-noise ratio that James Webb, at this distance, can only approach with extended observation campaigns. 16 to 24 additional hours of observation time, according to Madhusudan's team, could push the DMS signal to 5 sigma. That's not a huge investment in telescope time. For perspective, James Webb has spent longer than that on individual observations of nearby galaxy clusters. Whether K2-18b gets allocated that time, in a competition for telescope hours that involves hundreds of research teams worldwide all competing for a single instrument, is a scheduling and priority question as much as a scientific one. The extremely large telescope, currently under construction in the Atacama Desert in Chile and expected to begin science operations within the next few years, will eventually provide ground-based high-resolution spectroscopy of K2-18b that could, in principle, distinguish between DMS and the overlapping sulfur-bearing molecules that current James Webb resolution can't fully. Higher resolution means narrower spectral windows, which means cleaner molecular identification. That instrument isn't ready yet. When it is, K2-18b will almost certainly be among its first targets. James Webb is still operational, still pointing at targets, still returning data that dozens of independent teams across multiple countries are analyzing simultaneously. K2-18b's star system has now been observed by James Webb's 3 main spectroscopic instruments, NI-IRIS-S, NI-IRIS-S, NI-IRI-E, across near-infrared and mid-infrared wavelengths. The full picture of what those observations show is still being processed and argued over in real time. None of this is finished. The case is open, and it's being worked on right now. There's a version of how this ends that's straightforward. More James Webb data comes in, the signal either strengthens or disappears, and the question gets answered. Clean, clinical, resolved. But the history of this search, not just K2-18b, but the whole decades-long attempt to detect life beyond Earth, doesn't suggest clean resolutions come quickly. ALH84W1 took 28 years to reach non-consensus. The detection of water vapor on K2-18b by Hubble in 2019 was treated as major news, then quietly absorbed into a much larger and more complicated story 3 years later. What looks like a discovery in one year becomes a data point in someone else's follow-up paper the next. What's different about K2-18b is the specificity of what's being debated. Not might this planet have conditions for life. That's already been answered in the affirmative. The confirmed science on this planet, the ocean, the methane, the carbon dioxide, the hydrogen atmosphere, all of that points toward a world where the chemistry of life is at least plausible. The argument now is purely about one signal, one gas. Two instruments detected it. Multiple teams analyzing the same data say it disappears under different processing choices. That's not the same as, we found nothing. It's also not the same as, we found life. It's something stranger, a signal that is simultaneously real and not real depending on how you look at it. A molecule that only life produces, appearing exactly where you'd expect it if life existed there, at concentrations that only make sense if something biological is producing it, on a planet that fits every model of a world that could support life. And yet every attempt to lock down the confirmation runs into the limits of what the instruments can resolve at this distance. 124 light-years. That's how far the light has to travel to reach Webb's mirrors. In that distance, a signal that might mean everything gets smeared and blurred and noise-contaminated enough that three separate teams of professional astronomers look at it and reach three separate conclusions. The ocean is there. The chemistry is right. The telescope found the molecule. The molecule is disputed. And James Webb is still watching. If you've got a theory on this one, whether you think the signal is real, whether you think NASA knows more than they're saying, whether you think the ALH84W01 comparison means this disappears in 5 years or gets confirmed next year, drop it below. Genuinely want to know what people make of this one. And if you want to follow what happens next with K2-18b, with James Webb, and with the other targets nobody's talking about yet, subscribe and hit the bell. More of this coming soon.